So in this video, I'd simply like to discuss some criteria that I use to help me to decide, should I find the volume of the solid of revolution using method of washers, or would it be better to use method of shells? Now, I find personally that I tend to prefer method of washers just because it's easier for me to mentally conceptualize it. It's easier for me to draw the cross sections using method of washers. But sometimes being so narrow in one's scope can really get you into trouble. And to give you an example, let's suppose that we consider the problem of spinning the following region along the following axis. Let's say that. So here we have a triangular region, and let's say it's this fellow here bounded between the x-axis, the green function, and the red function. And let's suppose that we were spinning that region around the x-axis. Now, I am inclined, of course, to use method of washers because that is my favorite method. But I'm going to run into a problem where as you pass across this corner here, as you pass across this corner where the blue and the red function meet, the radius function is going to change dramatically. So here, the radius function changes. Excuse me, I'm going to detach this tablet. The radius function changes at the corner. So what does this mean? This means that in order to actually find this volume, you would need two integrals. One integral where the radius function was given by the blue function, and a second integral where the radius function was given by the red function. So if I were going to use method of washers here, I would absolutely have to do two integrals to actually find that volume. One integral for the blue function being the radius, and one for the red function being the radius. Now suppose that I broke out of my comfort zone here, and decided to use method of shells instead, which meant that instead of taking a vertical bar and spinning it around, I took a horizontal bar and spun that around. What's nice about using shells in this case is that the function that's on the top and the function that's on the bottom are always consistent. So the height of this function is always going to be this red x value minus this blue x value. Top x value, rightmost x value, minus bottommost x value. And the radius is always going to be consistent as well. The radius will always just be y. It will not change. So because of that, we get to avoid using dual integrals. We would only need one integral to find the volume if I decided to use method of shells. Now another thing that would affect my decision making is suppose that I decided to make method of shells, decided to choose that method, and I went and I set up the integral, but maybe the actual integral itself is extremely complicated. Because of the square, those integral problems using method of washers can get very involved sometimes because f of x squared, g of x squared can get very big. So sometimes method of shells is preferable simply because the formula doesn't have a square in it, and it avoids a lot of algebra. Sometimes you can really avoid a lot of algebra. So let's consider the following exercise. Let's not actually solve this exercise, but let's just try and analyze what method might be the most convenient to use for this problem. So we have y equals x, we have y equals 2 minus x, then we have y equals 0. So here's our linear function, y equals x. here is our linear decreasing function, 2 minus x, and y equals 0 is on the bottom. So we're spinning this around the x-axis. So find the volume of this solid of revolution. The question is, if I were going to do this, what method would I probably use? So here is y equals 2 minus x. Now, once again, if I'm going to use method of washers, just as in the previous drawing, I'm going to need two integrals. I'm going to need one integral from 0 to 1, where the green function gives me the radius, pi x squared dx. And I'm going to need a separate integral from 1 to 2, where the red function gives me the radius. So pi red function squared. This is what washers would have me do. This looks to me to be fairly involved. First of all, to actually calculate the red interval, I would need to expand this 2 minus x squared. It would probably be slightly tedious, and then you have to take two antiderivatives and calculate two differences. A little tedious. Now instead, if I do method of shells for this problem, then both of these functions have a consistent top and bottom. So I could integrate from the lowermost y value, y equals 0, to the uppermost y value of y equals 1, 2 pi times the radius of the cylinder, which would just be y itself, and then the height of the cylinder, which would be the difference in the two x values, x equals y versus x equals 2 minus y. Now the topmost x is given by the red function. This is the largest x, so I would put 2 minus y in the lead. And then the bottommost lowest x value is given by the green function, so I would put x equals y in the back. Now, is this a beautiful, clean, simple, easy integral? I mean, it's not perfectly clean, but I think it is better than the method of washers alternative. You can clean up this quantity, this difference in the brackets quite easily, multiply through by y, find the antiderivative using power rule, and it's all very lovely and nice. So I would certainly personally be inclined to use a method of shells to actually find this volume myself.